the motivation of developing this platform is there was a group of statisticians and engineers who have spending years of research on this subject because the existing methods are archaic and they are trying to find the modern approach to analyze type of data. What you see here is a screenshot of a paper submitted to Archive and is currently under review by a journal. So a group of statisticians and engineers led by Professor Bill Meeker, who is the first author of this paper. And there are 5 statisticians on the authors list. And you can see my name is the 5th. Bill Meeker is a professor from Iowa State. And Luis is a professor from Louisiana State University. Francis is a professor from Washington State University. Ili Hong is a professor from Virginia Tech. The first 3 authors also the authors of a book known as the Statistical Method for Reliability Data, 2nd edition. And Bill and Luis were the author for the 1st edition. I'm a new guy, joined the team. I joined pretty late. And the Wayne and Balaji, they are engineers. Wayne worked at Medtronic for medical device, and Balaji worked at Honda Aero for aerospace and aviation materials. The research had been conducted for several years, even before I joined them. I'm the last one I joined them, as I mentioned. The work is to propose a modern way to analyze fatigue data, fatigue test data. So my plan, why this subject is important, I will tell some stories and mention some applications. Then I'll go to the background. I will just show a slide of what this data look like. And for people already analyze type of data, you should already know this. Then I will say something about why the existing methods are archaic. And even the people that are already in this area, you may not know why. Then we dive into why the proposed modern approach is right. And I will also follow by describing the data characteristics of this special type of data. And then I will go to what's available models are in the software, then go straight to the demo. This may take maybe 20 to 30 minutes. Starting with the stories. The first slide, this is a picture from an accident, the flight 243 from Aloha Airlines back in 1988. So what happened to this airplane is that it was flying in the cruise altitude up in the air. Suddenly, the roof of the fuselage got torn off. And the airplane lost pressure and had to dive down. Fortunately, the plane safely landed. I think only that 1 person died in this accident. There are many factors contribute to this accident, like maintenance and corrosions and other stuff. What is related to the fatigue is interesting. The interesting part is that these airplanes are different from many other airplanes that fly on the big continent. So you see this is Aloha Airlines. They are in Hawaii. And their airplanes don't have very long flight every day, like we see on the continent, big continent of North America. We see every airplane may just do 2 round trips every day. But for Aloha airplanes, they do very short flight between islands. So there are many takeoff, there are much more takeoff landing cycles than other airplanes flying over the big continent. So they have much frequent takeoff and landing cycles. Because of that, the way you can consider that cycle related to fatigue should be different from other airplanes. And this is one of the factors that contribute to how they do the maintenance and do inspections. And probably people made some mistake during the process. This is the second accident I want to illustrate. So this happened in 2007. This is a bridge across Mississippi River, I-35 West, just near, I think it's in Minneapolis. It happened at the rush hour in the evening. And I think quite a few people died in this accident. What happened to this bridge is that the picture on the right, there's a sheet metal plate, And this plate over time deformed and warped. There are reasons behind that, but I don't understand because I don't have the mechanical engineer background. But this contributed to this accident. Over the time, this plate is just had an issue of fatigue, and it was not addressed promptly, and end up with it breaks and this bridge collapse. This another accident happened in 2018, happened to Southwest Airlines. What happened to this accident is one of the turbine engine blade broke during the midair, and this broken blade shatters the casing of this turbine engine and broke one of the windows. There was one casualty in this accident. The failure of this blade is known as the low cycle fatigue, which means the things break at a higher stress at lower number of cycles. This kind of incident may not be preventable in the end, but according to the investigation, at least the housing unit should be strong enough to contain that damage so it won't damage the fuselage. And this is an animation that's related to fatigue. Now there's an application. That's the medical device. So this application is a stent in the artery. And so your vein blood expand, contract. And this device is designed for the lifetime up to 10 to 15 years. And if you calculate that number and how many heartbeats during these 10 or 15 years, that's in my calculation, I may be wrong, it's close to that's around 500 million. So this device should not break after 10 or 15 years or in that period and end up with a needle in your heart. So that will be dangerous. And this is everyday life. And this happened to one of our friends. The picture on the left is a front axle of a vehicle. And when my friend was driving on the highway, suddenly the car lost control and slid to the left because one of the axles broke. And fortunately for him, he was on the leftmost lane. So he did not bump up into other cars which were driving behind him or in front of him or outside. So that's fortunate. And it's a kind of scary thing if we think it back. The thing to the right, this is the image of a garage door spring, and that's happened to me a couple of months ago. The spring snapped, and I purchased a new spring when I moved into the house, and I probably replaced it 10 years ago. So the last spring lasts for 10 years. And the guy replaced the spring, asked me, do you want to upgrade to a better spring with a longer life? I said, by how much? He told me maybe about 100 or 200. That's considered as a small fraction of the entire price of the replacement. Then I ask how long it will last. Then they tell me that the old spring, which is designed for 7 to 10 years, and this one is designed to 15 years. Then I say, go for it. So this is related to my daily life. So I just tell the stories, and hopefully you can understand how important this is to the public safeties and also relate to our personal life. Then let's start with describing the data. For the people who already seen it, you know it. For the people who haven't, then I will explain it. So this is a typical S curve data. S stands for stress in this particular case. It also can be something called a strain. I'm not going to dive into detail about that. Let's suppose this S means stress here. And N means a number of cycles to event. Event can be failure or can be a sensor. Sensor is a name in some literatures, and in estimated literature is called the runout. So this data table has 3 columns. First column is stress. Second column is cycles to failure. The last column is censoring type. It's either runout at the first row is, or it's a failure at what's in the third row. If I plot this data in a software, it looks like this. And the stress is on the y-axis, cycle is on the x-axis. And both axes are in their log scales. And this is the convention of how to look at the SN data. The markers here, the dot markers here, are associated with failures. And the angle pointing to the right are associated with runout. That means these particular observations, they did not fracture or fail upon the time that we have the record here. It's around 700,000 cycles. So these are the runout, they did not fail. So represented by the triangle pointing to the right. Now I'm going to describe what are some of the characteristics about this type of SN data. I plot different sample data, and you have seen that there's 4 different plots here from 4 different sample data. Generally, you should see that you can draw a decreasing line through them, which are the red curves here. That makes sense because higher stress, the earlier the failure will be. So the line should be decreasing. Otherwise, that's be counterintuitive. So the first one you can see is you can draw a very nice straight line through them. For the other 3, a straight line may not be the best fit, but a curved line should do the work. The second type of characters is associated with something called asymptotes. Look at the one on the left. The dashed line represents a horizontal asymptote. You can see these dots. These dots are failures. And the points on the top left are associated with higher stress level. This particular one is for strain, the percentage strain. Strain is related to, I believe it's for the shape deformation. So the dots on the top left are associated with failures at higher strain. And as the strain goes down, the cycles to events gets larger and larger, and eventually it gets leveled out. And you can see there are no more failures beyond this dashed line, under that. And we can see there are runouts over here to the right. So it's approaching a horizontal asymptote. So this is the one case. The case on the right is similar, except I draw a dashed line vertically here. And for this line, for this data, if we can imagine a curve that goes through these dots, we can see the horizontal asymptote all the way to the right. But maybe there's the asymptote all the way to the top. If we draw that, I continue, and it may reach some point and will never cross to the left of this dashed line. So these are the characteristics about SN data that are specific about asymptotes. Now there are the third type of characteristic about this data, the spread. You can see that for the data sample data here, if you see a cluster of points by rows, these are a collection of specimens that measure their failure cycles at a specific stress level. And the first stress level is in the first group, the second stress level is second group, and so on and so forth. If you consider the spread of these dots at different levels, for this first example, you can see the spread is kind of small on the top left, associated with high stress. And the spread at the bottom are very wide, associated with the lower stress. And for the second data example on the right, the spread for the higher stress level compared to the stress associated with the lower stress level are kind of similar. So this is one way to look at data. And there is another way to look at data is look at vertically. There's exhibit 3 and exhibit 4. If we can imagine the spread vertically, for exhibit 3, the spread for the group that fails earlier, say before 50,000 cycles, the spread is roughly at the same scale that's associated with failures at the larger number of cycles. So they kind of keep constant. And then look at exhibit 4. If you can look at spread of the points associated with lower cycle failures and higher cycle failures, you can see the spread are not kind of same. The spread very, very widely for the lower cycle failures, but quite narrow for the higher cycle failures. So this is the third type of characteristics. Now let's talk about objective of analyzing this type of data. I have already shown you the spread. Why do we care about spread? So in the end, we want to know about two distributions. First is fatigue life distribution, which are the distributions that we draw density horizontally for every specific stress levels. The second objective is to get a fatigue stress distribution, which is the distribution we draw vertically, which is associated with individual cycles to failures. I want to mention that the word here, stress, and it's different from what I draw here from data, which is stress. They are different. Stress is a predetermined setting experimental variable or experiment factors, which is not random. But the strength is associated with the specimen. Every specimen has its own strength. The strength is not observable. We cannot tell exactly what the strength of that specimen is when I hand over the specimen to you. You won't be able to tell it. You have to measure it, but it's random, and then the only we can observe that is by two types of experiment. One is here, you can see here, but the only we can control is not random. It's just stress. And there are another way that I'm not going to mention that, which is not relevant to this development at the moment. But I want to bring attention that stress is a variable, life is a variable. Life is observable, stress is not. And the stress or the strain in the data, they are predetermined factors or effects. They are not random variables. So this is a very important concept you need to realize. So now, also what I mentioned about those concepts is related to this existing method. Why we call that archaic approach? This is one archaic approach. The first thing I said here is many existing methods treat stress as a response, cycle as explanatory variable to estimate fatigue stress distribution. That is wrong, because stress is not a random variable, and it should be a response, and cycle is random. It should not be treated as explanatory. But we will see how to estimate this fatigue stress distribution, even if it's not observable. We will go there. All right, the second mistake in the existing method is to ignore runouts or treat them as failures. The runouts are the angles pointing to the right here in the data. So the runout means the failure did not occur before this time, but it's possible it will occur after that point. So imagine that if we have some failures occur after the point, if it's really happened, for example, here and here, even beyond my screen range, if I draw them, you will have totally different idea by looking at the data if you have those failures. So this runout, this sensor data should be treated properly. You cannot just consider as failure. If we put dots here, what you can imagine about this model is totally different if we put the dots far to the right. So this is a mistake by ignoring runouts and treating them as failures. By treating them as failures or ignore them, many people just go straight ahead using least squares, because least square is commonly used tool for line through data points, regardless of what data points means, and also it's convenient. But least square won't be able to handle sensor data, won't be able to run outs. You have to think about other thing else other than least squares. In the end, many of these approaches separate the modeling of fatigue life and fatigue stress distribution. They model them separately. According to our research, these two distributions can determine each other mutually. That means if you know the fatigue life distribution, you don't need to derive the distribution for strength separately. It can determine that. And also vice versa. If you know the strength distribution, you can derive the fatigue life distribution directly. You don't have to analyze and fit a different model. They are the same. They are the same thing. They mutually determine each other. So as a contrast to the right, the modern approach, do it right. So cycles is the response, and stress is explanatory variable. Roundouts are censored observations, and we always use maximum likelihood inference to analyze this type of data. And in the end, the new approach models the fatigue life and fatigue stress distribution simultaneously. All right, so this is what models are available in the JMP 18 fatigue model platform. I want to point out there are two categories. There are two categories and 6 different S-N curve relationships. The two categories are defined based upon which distribution you specify. As I mentioned, the fatigue life distribution and fatigue stress distribution can determine each other mutually. If you specify one, you can induce the other one. So the first category is only specify fatigue life distribution and induce fatigue stress distribution. And two S-N curves under these categories are called Box-Cox log linear sigma models and also Baskin models. The second category is specify fatigue stress distribution and then induce fatigue life distribution. The 4 S-N curves under these categories are named as Coffee-Manson model, Nishijima model, Coffee-Manson zero elastic slope model, and the rectangular hyperbola model. I will demonstrate one Box-Cox, Baskin, Coffee-Manson, and Nishijima. Remember that I mentioned distributions. All these 6 are S-N curve relationships. They are not distribution yet. So to specify a distribution, for example, either life distribution or the strength distribution, we can put a distribution on top of it. We have 4 options: log normal, variable, logistic, and Frechet. Log normal and variable are most commonly used ones. So totally in this platform, we have 4 times 6, 24 models in total. These are the picture of what these curves, these S-N shape, that's S-N relation look like. There's a dividing line, red dividing line. On the left, these are the models associated with categories that specify fatigue life distribution. The first one on the top, this is Box-Cox log linear sigma model. You can see there's a curve that goes through these points, and we specify this density curve, which is horizontal, with associated with fatigue life. And the dashed line represents the fatigue stress density. So we specify the distribution for the fatigue life and induce distribution for the fatigue stress. The next S-N curve relationship is Baskin. For Baskin, it has a straight line goes through data points on this log scale paper. The 4 plots to the right side of this red dividing line are the models associated with the category that we specify fatigue strength distribution. I draw a density curve here, which is vertical. So this is the density curve associated with fatigue strength. Then we derive the density that's associated with fatigue life. And you can see that for this first one, Coffee-Manson model, it's a curved line. It has 2 asymptotes, but neither of the asymptotes are vertical or horizontal. Then there's a Coffee-Manson zero elastic slope. This is a special case of a Coffee-Manson model. It has a sloped asymptote, but has a horizontal asymptote on the bottom. The next one is this Nishijima model. It's a curved line, goes through the data points. It has a sloped asymptote and also a horizontal asymptote on the bottom. This is a rectangular hyperbola model. It has both a horizontal asymptote and also a vertical asymptote. Now the relationship among them is I mentioned that Coffee-Manson zero elastic slope model is a special case of Coffee-Manson model. There's a limit that's this asymptote, sloped asymptote can be totally flat that end up with being a model like to the right. And the rectangular hyperbola model is a special case of this Nishijima model. As this sloped asymptote go vertical to the limit, it ends up with the model to the right, which is the rectangular hyperbola model. And now there's a very special model in this plot, which is this Baskin model. This Baskin model is a special case of all these three: Box-Cox model, Nishijima model, and also this Coffee-Manson model. So this is kind of unique for Baskin model. This is a special case of both of these three. All right, so this is a list of available results. After you get fit model, you need to get the result out of it. What you can get from the software, these are a list of things. First is the plot for data, then the model summary. For model summary, you can get parameter estimates, the standard errors, and the word type confidence intervals around the parameter estimates. Then you got these plots of density curves, quantile curves for both fatigue life and strength distributions. And you also can get the fatigue life and fatigue strength cumulative density functions and also quantile profilers. In the end, if you really want to get the likelihood-based confidence level, you should use this function, customer estimations. So these are the reports available from the software. Now I'm going to go to the demo.